It says calculate the electric field intensity. Calculate the electric field intensity between two plates of potential difference 6.5 volts. Potential difference 6.5 volts when separated by a distance of what? 35 centimeter. So you have potential difference of 6.5 volts, and then you have the distance to be equals to 35 centimeter. So electric field intensity E is to be calculated. All right, so your electric field intensity is your force per unit charge between two charges. So let's say you have a charge moving from point A to point B, separated by what? A distance what? X. Are we together? So electric field intensity is your force per unit what? Per unit charge. That's the first formula you need to know. So this one can equally be called electric field intensity or electric field strength. It's the same thing, just in case you see it in another question. Okay, so force per unit charge, that's what's the basic formula of electric field intensity. So how do you relate that with potential difference? Okay, so you know another formula here, Coulomb's law, that says that your force is equals to kq square, or let's say q1 q2 all over what? R square. Coulomb's law says that when you have the force between two charges, are you getting, is directly proportional to the product of their charges and inversely proportional to the square of their distance apart. So you have a charge here q1, you have a charge here q2. So the force between the two of them is directly proportional to the product of their charges and inversely proportional to the square of their distance what? Apart. Okay, so when you do that, you know, it's an inverse, is a relationship. So when an equality sign is introduced, a constant is equally what? Is introduced. When a proportionality sign changes what? An equality sign, a constant is what? Is introduced. That's why you have that K there. Okay, so this is another formula. This is Coulomb's law. Okay, so now if these coulombs, the charges are identical, then you are going to have, if the charges are identical, if Q1 is equals to Q2, which is equals to Q, then you have your force to be equals to kq square all over what? R square. Okay, so this is another formula worthy of what? Of note. Then there you can know that your F over, from here, one of these Q comes here, F over Q, this will be equals to kq all over what? All over R square. Don't forget what I told you. Electric field intensity is F over Q, that's force per unit charge. Okay, so here now you're having force per unit charge. It means you have another formula for what? For electric field intensity. So but F over Q is electric field intensity. It means that he is equal to kq all over what? All over R square. You have that. Okay, now the work done, we all know that work done is force times what? Force times distance. Okay, that's your work done. First times what? Times distance. Okay, so now your force times the change in distance between this point and what? And this point. So you have change in what? Change in x. Okay, now if I divide both sides by q, then I'll have, if I divide both sides by q, I'll have, you know, in mathematics, when you do something to the left hand side, you do the same thing to the answer, right hand side. You haven't changed the equation. So but because I have where I'm going, so if I divide both sides by q, I have w over q equals to this. I have over q. Okay, so there I have w over q is your potential difference. Your potential difference is W work done per unit charge. Okay, now I have my potential difference, which is work done per unit charge, to be equal to, let's say I call it change in V. Sometimes you see that as what? Minus V, quite alright. Okay, so we have change in V to be equals to this, which is change in V, to be equals to force per unit charge times what's it called? Change in X. Change in X. So my potential difference, change in V, equals to force per unit charge, don't forget, is your what? Electric field intensity times change in what? X. So it therefore means that my electric field intensity equals to the potential difference divided by what? The distance. Okay, so like I said when I was solving question number 1, no one would ask you to prove these formulas in your Jamb. You need to have them handy. You need to know the formula that you need to have. So I'm trying to break it down just for you to be able to apply this same solution to another question. Are you getting it? So you have the necessary formula, some of the formula lists that you need under electric field intensity. I just broke it down for you so you can pick them and use them for another question. That's the idea. Not like you will be doing this in your Jamb. Please don't do this. It's a time waster. All right, so just pick this formula. You need to have it handy. Electric field intensity is force per unit charge. Electric field intensity is potential difference over distance. Are you getting it? You know that your potential difference is work done per unit charge. Are you getting it? You know that your force is equal to kk square over r square. Okay, if the charges are identical. So you need to have those formula handy. So when they ask you, you just apply it straight on. Here you have the potential difference has been given to be equal to 6.5 volts. Okay, so your change in V is 6.5 volts and your distance is what? 35 cm. So you need to ensure that this goes to the SI unit. This is in centimeter. You need to take it to meter. Okay, so this is equals to 35 divided by 100. So that takes me to 0.35. That takes me to 0.35. Okay, so now my electric field intensity, my pen, electric field intensity equals to change in X again, change in B over change in X, which is equals to 6.5 divided by what? 0.35. So if you do this for this calculation, where you are dividing 65 by 35, you know that it will go once. You can't get to 65. So when you're writing Jamb, there are certain things that you don't actually need your calculator. 35 won't go in 65 2 times is 1. Then you look at your options. The only answer that is starting with 1 is one of the options. Others are 5, starting with 5 and others. So even without calculating others, you know that you have your answers already. So but if you look at this is going to be 18.57. so if you divide this will give you 18.57. Okay, so the units, force per unit charge is what? Coulombs, Newton per what? Per coulombs. Force per unit charge is, force is Newton and the coulombs is charge. So you have Newton per what? Per coulomb. That is your answer. Okay, so the question number 4 says, why do soldiers march disorderly on a bridge? Why do soldiers march disorderly on a bridge? They are moving together on a bridge, but they don't march at the same rhyme. You know soldiers, you know when they march very rhyme. But when they march on bridge, they march disorderly. Why did they do that? This is to avoid what we call resonance. What is resonance? Resonance occurs when a vibrating object sets another object into vibration as a result of impulse received from the one vibrating, and both of them are now vibrating with what? Natural frequency. Okay, so if soldiers should march at the same rhyme, are you getting it? They are going to call a sort of vibration. Are you getting it? Which could set into the same natural vibration of the bridge. and if that happens, you call what we call resonance, and it will be a total collapse. Okay, so they are doing this to avoid what we call resonance, so that the bridge doesn't what? Collapse. As a resonance occurs when a vibrating object sets another object into what? Into vibration, as a result of the impulse received from the one vibrating, and both of them now vibrate to what we call natural frequency. Okay, so soldier needs to match this so that they don't set this thing into a uniform vibration. All right, which could now lead to what? The same vibration with yours, the natural vibration of the bridge, and that will cause resonance. Okay, so that is the essence. Okay, so the option says to prevent resonance on the bridge. I've just told you there's your answer. To set the bridge into resonance, if they want, they will match at the same rhyme. Okay, and then another one said to make the bridge collapse. No, they don't want to do that. And then to spread their weight evenly. That's not what they're doing. They're preventing a resonance. Okay, so question number that's question number 4, to prevent resonance. Okay, all right, so question number 5. Question number 5 says calculate the upthrust on an object of volume 50 centimeter cube, which is immersed in what? In liquid of density 103 kilogram per what? Per meter cube, given G to be equal to 10 meter per second square. Okay, so we're to calculate the upthrust on an object of volume. Volume is 50 cm cube. Okay, so liquid immersed in density. The density, which is your rho, is given as 103 kilogram per what? Per meter cube. And then your acceleration due to gravity, G, is given to be equals to 10 meter per second square. Okay, so your upthrust, this is under Archimedes principle, that says that a liquid, an object displays the weight of itself in which, from the liquid in which it floats. When an object is partially or wholly immersed in a liquid, are you getting it? It's the same. The volume of water that is going to displace, or the liquid it displaces, is equal to the weight of that object itself. Okay, so that is under Archimedes principle. So upthrust here is equals to the weight of the object. Are you getting it itself? So here we have some of the formula that you need here. I'll just list them as usual, but like I told you, you don't need all this celebration in your. So your density is mass per unit volume. Okay, so your mass equals to rho times what? Times V. Okay, your mass equals to rho times V, and your weight is going to be mg, which is the same thing as rho vg. Are you getting it? So this is your upthrust. So you can call it your here you have upthrust, viscous drag, and all the things that you discussed, viscosities and all of that, but I'll just limit it to this for now. So we have weight to be equal to rho vg, and then here I've been giving, so this is equals to my upthrust. So this is equals to my upthrust is therefore equals to rho, that's the density, 103 kilogram per meter cube, times V. This has to go through SI units. This is centimeter, so you are going to have it to be equals to 50 times 10 raised to power minus 2, that's divided by 100. There are 3 of them because it's centimeter cube. There are 3 centimeter in centimeter cube. Then I'm going to have it to be equals to raised to power 3 times, we're asked to take rho and G to be 10 times 10. So if you do this, you would see that you have this to be equals to 103 times 500 times 10 raised to the power minus 6. So this would give you 0.5. This will give you 0.5. You dial that, so you have 5. This is 10 raised to the power minus 4, quite right? So 5 times 103, that's what you have. 5 times 100 is 500. 5 times 15 is 515. Are you getting it? Divided by that, so you have that to be equal to 0.05. So you have this to be equal to 0.5 Newton. Okay, this should actually be 0.05, I guess. Okay, yeah, 0.5 Newton. Do your calculation. So your options, you have 0.8 Newton, you have 2.5 Newton, you have 0.5 Newton, and then you have 1 Newton. So this is the closest to it. That is should be an approximate answer, not the real answer. So you have question number 6 now. Now question number 6, you have, under what condition are cathode ray produced in a discharge tube? So you have a discharge tube and you have cathode ray. So you have under what condition is it produced? When you have a discharge tube, okay, when it is energized under high velocity, are you getting it? So you have your negative terminal, which is your cathode. You have your positive terminal, which is your anode. Are you getting it? So when this tube is again energized, you have the energy knockoff electron from that element. Are you getting it? Which travels in that medium. Are you getting it? So this, when it strikes the negative terminal, are you getting it? This emits some sort of radiation from that negative terminal. You know, the negative terminal is called the cathode, the positive terminal is called the anode. Because these rays are coming from that negative terminal, we call it the cathode rays. Are you getting it? These cathode rays, when it goes to anode point, are you getting it? It's going to be repelled. Are you getting it? So when it repels it, so it's not going to absorb it, it returns back to the negative terminal. All right. So in essence, for you to produce a cathode ray, you have high voltage. Are you getting it? And what? Low pressure. When you have a low pressure and high voltage, this high voltage knocks off electron from the element in the tube. This travels and knocks off when it strikes the negative terminal called cathode, and some sort of radiations comes from it. These radiations are called what? Cathode ray. Are we together? So that's how cathode ray is produced. You can have this is just a summary of it, so to speak. Okay, so under low pressure and high voltage. So you have the options you can pick from your options. Cathode rays are produced under what? Under high voltage, but what? Low pressure. Okay, that's question number 6. Now question number 7, we have